Hello everyone, I'm Adam. In this problem, we're going to evaluate our line integral using the fundamental theorem of line integrals, where we're given our vector field f. Here f is equal to cosine x times sine y times the unit vector I plus sine x times cosine y times the unit vector j. And our curve c, we're told, is a line segment from some initial point at, say, 0, negative pi, to some terminal point 3 pi over 2, pi over 2. So to use our fundamental theorem of line integrals, right, first we have some conditions that we have to check. Now, here's kind of a bullet-pointed list of our fundamental theorem of line integrals, right, and albeit it looks scarier than it actually is. So if we take a look at this, first thing is that we need our curve C to be a piecewise smooth curve, right? So, and it's also can be given by some parametrically defined equation here, this R of t, where t is between some a and b. Now, based on what we're told, we really don't have to worry about this equation, because what are we told? It's a line segment from one point to another point, right? Where also these points are in the xy plane. So a line segment is continuous and it's smooth. A piecewise smooth curve is a curve that can be broken up into finitely many pieces, where after connected, it makes a completely smooth curve, which a line segment, we already have that. So condition one is kind of met. Next, our vector field, right, which in general we can write as f equal to some m times I plus n times j, is conservative. And we'll get to the conservative point in a moment, or part in a moment. But we need that m and n to be continuous. So our m and our n are essentially respectively our cosine x sine y is m, and sine x cosine y is n. Well, sine and cosine are continuous functions for all real numbers anyway. So our m and n are continuous. So that's met. Now lastly, we need f to be conservative. Okay, so basically, in the process of trying to find our integral, we're going to answer this question. So assuming this is true, what we have is that our line integral is going to be the integral of the gradient of some potential function f, okay, where the integral can be evaluated as f of x of b and y of b, which is essentially the endpoints of our curve c, which again, this looks more cumbersome than it needs to be. These endpoints are essentially the endpoints of our curve right here. And then minus f evaluated at the initial points x of a, y of a, which is our initial points right there, or initial point right there with x and y coordinates. Now the conservative part is going to come in when we find this potential function here. So if a potential function exists such that f is equal to the gradient of that, then that means f is conservative. So we'll kind of be showing that in that process of finding f. Okay, so let's get started. So what we want to do is find, say, our potential function, say f. Okay, and how are we going to do this? Well, for starters, we know that our potential function f of x of y, which is equal to the integral of the partial derivative of x, of f with respect to x, okay, which is equal to, right, going to be essentially our m part of our vector field f. So the integral of cosine x times sine of y, right, dx. So taking the antiderivative of this with respect to x. And so we just have a cosine as a function of x, so sine of y treated as a constant. So this is just going to be equal to sine of x times sine of y. And now plus some integration constant. But it's not going to be, again, some general constant, right? Because here we had a function of treating everything as a function of x. Anything as a function of y would be treated as constant as well. So I'll just put some general, say, g of y, just maintaining that whatever constant on the end could still be a function of y. So we're going to find it there, f, but we also kind of fill in the blanks as far as what maybe g might be. We're going to look at f of xy being the integral of the partial derivative of f with respect to y, dy, right, which is going to be the integral of our essentially n part of our vector field f. So integrating we have sine of x times cosine y, dy. Where same thing, we're taking the integral with respect to y, so sine of x here treated as constant, so this will just be equal to, say, sine of x times sine of y, and plus, say, some constant that could be a function of x, so we'll just write it as, say, some h of x. Okay, now we take a look at this, right, and seeing that after we took our integrals, we got both the same thing, sine of x times sine of y, and sine of x times sine of y. Since those are the same, that does kind of confirm that this g of y is just going to be some constant, not a function of y, and our h of x, again, some constant, not a function of x. So clean this up, put it together. So our potential function, f, right, is just going to be equal to sine of x times sine of y, and we can just write it plus, say, some general constant k. Okay, so in finding that, we've confirmed that f is conservative, we have all the other conditions met, and now we can take our line integral. So we have that our integral is just going to be equal to, so looking at the end, so again, f evaluated at this terminal point. So that's just our point, 3 pi over 2, pi over 2. So minus, right, f evaluated at 3 pi over 2 and pi over 2 minus f evaluated at our initial point, which we have as 0 and negative pi. So we'll go ahead and just find what that is. So that is equal to, so we're going to have sine of x, or sine of 3 pi over 2 times sine y, or times sine pi over 2, and minus f of 0 and negative pi, or sine of 0 times sine of negative pi. All right, and what do we get? So sine of 3 pi over 2, we have negative 1, sine of pi over 2, we have positive 1, and minus sine of 0, we have 0, and sine of negative pi, we just have 0. So it looks like we just have negative 1 times positive 1, so our line integral is equal to negative 1. And there we have it. Thank you very much.